Let's see here. There you go. All right, so first things first, looking at this equation of the plane. So I'm going to rewrite that equation as a matrix equation. So I can write it as like 1 minus 3 minus 4 times vector x, y, z equal to 0. So when I write the equation in this form, so it looks like a times vector x equals 0. Then here what we see is that the solutions to this equation actually constitute the null space of this matrix A. So then that's what they'd be referring to in part A, that the plane described by this equation is really the null space of this 1 by 3 matrix, 1, minus 3, and minus 4, okay? So then getting the basis of the plane by finding the special solutions. So there, that would just be the process of like, parameterizing the solutions. So in this case, you have two free variables. So what I would do is I would make y and z my free variables. And then x would be just 3y plus 3s plus 4t. And then here, if I look at the well, okay, so if I write this out in a vector form, I could write it as s times 310, and then plus t times 401. Okay. So this shows that the plane is all linear combinations of these two vectors. So then these would have been your two special solutions, and they would have constituted the basis for the plane, or a basis for the plane. Okay. And then I guess like for part C, so since the plane was the null space of A, that means the orthogonal complement of the plane would have been the orthogonal complement of the null space of A. And in general, we know that the orthogonal complement of the null space would be the row space. Yeah. So in this case, since A is just one row, then that means that one row vector, which I'll write as a proper vector, so like as a column. So this would have been a basis for the row space, and hence a basis for the orthogonal complement of the plane, okay? All right, so I don't know if you guys had any questions about that one. Mm-hmm. Okay, so there were these orthogonality relations between the fundamental subspaces of a matrix. So in general, the row space and the null space were orthogonal complements. So here, because the plane was the null space of this matrix A, this 1, -3, -4 matrix. Yeah, so the orthogonal complement, that is correct, yes. So the orthogonal complement of the plane was the orthogonal complement of the null space, which is the row space. Now, so the row space is technically the column space of A transpose. Okay. So that means if I were to transpose this matrix A and then look at what its column space is. So here its transpose is just one column. So like this one column vector would have been a basis for the column space of A transpose. And that's why I use it as the basis for the row space. Okay. All right, and then yeah, also that so just like how the row space and null space are orthogonal complements, the column space and the left null space are also orthogonal complements as well. Okay. All right, let's see here. So I'll go ahead and move on to the second problem then. Okay. Let's see here. So looking at part A for this problem, part A is kind of the same as what we did in part 1. So, oh, it's the same plane. Oh, okay, that's cool. So it's the same equation, so it's the same plane as before. So we already found a basis for the plane in problem 1b. So the basis was, let's see here, it would have been 3, 1, 0 and 4, 0, 1. Okay. So that's actually what we found in question 1b, basis for the plane. Okay. So in order to find the projection matrix that will project onto this plane, so in general, to find a projection matrix that will project onto some subspace, and the procedure for that was to find a basis for that subspace. So here we already have the basis for W. We're going to place those basis vectors into a new matrix as columns. So I'll go ahead and call that new matrix A. So then you can calculate the projection matrix after that by using this formula where it would be A times A transpose A inverse and then times A transpose, okay? All right, so let's go ahead and do that computation. Let's start with A transpose A. So that's A transpose and then times A. That's going to be, let's see here, 9 plus 1 is 10. 12 12 again. 16 plus 1 is 17. Okay. So then to get the inverse of this matrix, I'll use this formula for the inverse of a 2 by 2. A, B, C, D inverse, it was 1 over the determinant. And then it's a D, A minus B minus C. I guess I can go ahead and mention it now. This formula for the inverse of a 2 by 2 matrix is actually the 1 over determinant times the transpose of the matrix of cofactors of the 2 by 2 matrix. So if you guys remember that formula for the inverse of a matrix, when we talked about determinants, this is actually that formula just for the 2 by 2 case. All right, so then the inverse of H transpose A is going to be, let's see here, 170 minus 144 is 26, I think. Okay, so we have that, and so now we'll compute A times the inverse of the transpose, or inverse of A transpose A, and then times A transpose, and then all of that should give us the projection matrix for part B. So let me see here. I'll multiply these two first. So that'll be 51 minus 48. So that'll be 3. And then negative 36 plus 40 is 4. And then, I guess, next we'll take the identity and times the matrix, so it'll just be itself. So then we'll have this matrix now times this. So that would be like 9 plus 16 is 25. And then we'll do, all right, so I'll get the first column first. So 17 times 3, so 51 minus 48 is 3. And then negative 36 plus 40 is 4. And then when I multiply with the remaining two columns here, this is just an identity matrix. So multiplying this with that should just give me this matrix again. So I'll just copy it down for the remaining two. Okay. So then, yeah, this should be the projection matrix that will project onto the plane. So then to find the projection of vector 3, 2, 1 onto the plane, we would just take the projection matrix that we computed and just multiply it with the vector 3, 2, 1. So I guess we can do that real quick. So 75, 81, 85, I think. And then 9, 33, 21, if I did that right. And then 12, negative 12, so negative 2. Okay. So then that should be the projection of 3, 2, 1 onto the plane, all right? Okay, now let's see here. All right, yeah, let's go ahead and move on to the next question then. Okay. Okay, so yeah, so here we're trying to fit a parabola to these 5 data points that we have. So let's say the formula for our parabola is c plus dt plus et squared. So we want to imagine a parabola that when we plug in these values for t, we're hoping to get these values for the polynomial. So then if we plug these in for t and plug these in for the polynomial, that will give us a system of equations. So let's see here, for the first one, when y should be 0 when t is negative 2. So I'm going to plug negative 2 for t over here. And I'm going to do the same thing for the remaining data points. So the next one is y should be 0 when t is negative 1. Next one is that y should be 1 when t is 0. When t is 0, it'll just be c. Then when t is 1, y should be 0. And then when t is 2, we want y to be 0 again, okay? So if there were a parabola that passed through all 5 of these points, we could solve for the coefficients of the parabola by solving this system of equations, okay? Now, however, what's happening is that there is no parabola which actually passes through all 5 points. So what we'll do instead is we'll find the parabola that comes closest to fitting these 5 points, all right? So to do that, we'd find the least squares solution to this system of equations. Let's very briefly talk about what that would be. So when you have an equation ax equals b, and if this equation has no solution, then the least squares solution, which I'll call x hat, it's the vector that comes closest to solving this equation that had no solution. And in order to find the least square solution, you can find the least square solution as being the solution to the equation A transpose AX equals A transpose B. Okay? You can remember this equation by just taking the original equation and just multiply both sides by A transpose, and that gets you this system of equations, okay? All right. So here we have a system of equations. I'm going to rewrite it in the form AX equals B. Okay. And so as I was saying, this equation will have no solution since there is no parabola passing through the 5 points. So we're going to find the least square solution instead. So to get the least square solution, we'll need to calculate A transpose A as well as A transpose B. So let's do that first. Let's see here. I'll write it down here. So let's see, that's going to be 5, negative 2, negative 3, negative 2, so 0. Let's see here. 4, 5, 0, 6, 10. We just talked about how, when I was talking about SVD earlier, I mentioned how A transpose A is always symmetric, so don't need to worry about those. So for this entry, second row times second column, it's 4, 5, 6, 10 again, I think. And then let's see here, for this entry, it'll be second row, third column, so negative 8. I think that's 0 again, I guess. And so then this one will be 0, and then the last entry will be 16, 17, so 34. All right. So we have A transpose A. That gets us the left-hand side of this system of equations. We also need the right-hand side, A transpose B, so let's do that next. So we got that, and then times B. So that would be equal to the third column, 1, 0, 0. Okay, and so then to solve this system of equations, A transpose AX equals A transpose B. We can solve that system of equations by setting up the augmented matrix. So here's A transpose A. I'm going to augment it with the right-hand side, A transpose B. And then we just want to try to solve this system of equations now. Let's go ahead and just do one row operation. I'll do row 3 minus 2 of row 1. So that will give me 0, 0, and 14. Okay. So then, oh, I forgot the right-hand side. Okay, I was like, I'm missing something. So on the right, we would have had 0 minus 2. So that would be -2 down there. And then here, it's already upper triangular, so I just write out the system of equations. Let's see, like, I guess we'll do like 5. I guess I'll do C hat plus 10 E hat is 1. Second equation, I'll do 10 D hat is 0. And then the last one is 14 E hat is -2. And I guess it's not super important, but I'm just using C, D, and E hat just because I was using X hat for the least square solution earlier. So if X is C, D, E, I was just thinking that X hat would be C hat, D hat, and E hat. Okay. But from here, that means D hat would be 0. E hat would be -2 over 14, so -1 over 7. And then C hat, solving for C now, would be 1 minus 10 E hat, and then all over 5. 17 over 7. So 17 over 35. So then now that we have the least square solution, using those as the coefficients, we can now write out the equation of our best fit parabola. So I guess P of t equals, or maybe y equals. So it would be C hat plus D hat times t, and then plus E hat times t squared. Okay. All right, so any questions about that? Yeah, it's not bad, just a bit of computation, but yeah, it's not bad. All right, so yeah, let's go ahead and move on to the next question. Okay, gotta do Gram-Schmidt. Okay. So let's talk about how Gram-Schmidt works. So if you have some number of vectors, I guess I'll illustrate with just 3 vectors. So let's say you had 3 vectors, v1, v2, and v3. So they form a basis for some space, but you want to, from this basis, you want to create an orthogonal basis for that same space. So that's what Gram-Schmidt does, is it takes a basis and returns a new basis, which will be orthogonal. And these new orthogonal vectors, they'll still span the same space as the original vectors. And there's just some formulas that you need to know for this. So W1 is going to be equal to V1. W2 is going to be V2 minus its projection onto W1. And here I'll go ahead and write out the formula for its projection onto W1. So we'll do V2 dot product with W1 over W1 dot product with itself times W1. Okay. So here the idea is subtracting its projection onto W1 will leave you with something that was orthogonal to W1. And then W3 is going to be similar, but we'll take V3. And now we want to subtract V3 and minus its projection onto W1 and W2. So this would be the projection of V3 onto W1. And then here would be the projection of V3 onto W2. Okay. All right. And then hopefully you wouldn't have any more than 3 vectors because it gets pretty long after that. But if you do need like W4, it would be V4 and then minus its projection onto W1, W2, and W3. Okay. All right, so then in this case, W1, the first vector, would have been all right, so are you guys okay with me skipping this one once you have the formulas? Okay, all right, sounds good. So let's look at the next one. Okay. Okay, so for this one, we need the determinant of 2B transpose and then times A inverse. So first, using some properties of determinant. Okay, well, I guess first, so on the inside, that's just a 2 times B transpose times A inverse. Okay. All right, now first, properties of determinant. This 2, we can factor it outside of the determinant. But when we factor a constant out from the determinant, it has to be raised to a power determined by the size of the matrices. So since these matrices are 4 by 4, when I pull out the 2, it has to be raised to a power of 4. Next, we have determinant of B transpose times A inverse. So then, using other properties of determinants, that's the same as determinant of B transpose, and then times determinant of A inverse. And then finally, 2 to the 4th is 16. Determinant of B transpose is the same as determinant of B. And then determinant of A inverse is just the inverse of the determinant of A, or just its reciprocal. Okay. So then at this point, we'd want to calculate the determinants of A and B. And then that would pretty much be it. So fortunately, there's lots of zeros, so it's relatively quick to calculate the determinants. So let's say if I want the determinant of A first, let's just do cofactor expansion along the first row. So all we really have is, I guess, minus -2. So the minus -2 is, let's see here. Well, let's see here. I guess, let's see here. You could do that, but I guess it might be easier to think of it like this. Let's see here. Oh, no, that doesn't work. Okay. So I'll just go ahead and do it. So minus -2 times determinant of this remaining 3 by 3. And then let's see here. So that'll be 2 times. And then if we do another cofactor expansion of this, it looks like it'll be times 3 and then 0 minus 4, 5, 0. So it looks like it's going to be 2 times 3 times 20. So I guess that's going to be 120 altogether. And then just real quickly getting the determinant of B. Again, let's just do a little bit of cofactor expansion. So expanding along the first row will give us 2 times, and then we have this remaining 3 by 3. And then minus -1, so plus. And then we'll have this for the remaining 3 by 3. All right, and then let's just quickly compute that. So it'll be, I guess I'll continue down actually. So then for this one, we're going to have, I guess I'll do another cofactor expansion along the first row. 2 times 2 minus 1 minus 1, 2. And then minus and negative, so plus minus 1 minus 1, 0, 2. And then this one's just going to be minus, going along the first column, it'll be just this. And then you can work out the determinants. And then once you get determinant of B, you also have determinant of A. So then you just plug everything back up here, and that will give you the determinant of 2B transpose A inverse, okay? All right, any questions about that one? All right, yeah, let's continue to the next one then. Oh, okay. Yeah, so we have this matrix A right now. And so there's, I guess, 2 parts to the problem. First is using Cramer's rule to solve a system of equations. So let's talk about how that worked. So if you have the equation AX equals B, and if the matrix A is invertible, then Cramer's rule gives an explicit formula for getting the solution. So Cramer's rule, basically it says x1 is the determinant of some matrix, which I'll call A1, and then divided by the determinant of A. Now this matrix A1, it's the matrix that you get by replacing the first column of A with B, the right-hand side of your system of equations. So I'll say A1 is A, but first column is replaced with B. Okay. And then likewise, X2 is determinant of A2 over determinant of A, where A2 is the matrix A, but the second column is replaced with vector B, and then kind of so on and so forth. So for this problem then, to get the solution using Cramer's rule, X1 would have been, let's see, I'm going to take A, but replace the first column with B, which was 0, 0, 1, okay? And then I'll copy down the remaining, the rest of A as it was. So it'll be that over the determinant of A. And then X2 would be, replace the second column with B. And then divide by determinant of A. And then to get X3, replace the third column of A with B. And then divide by the determinant of A. All right. So because there's a nice column with lots of zeros in each of them, we can get this pretty quickly. So X1 is going to be 4 over the determinant of A. X2 is going to be, I think, -2 over determinant of A. X3 would be 2 over determinant of A. And then let's go ahead and calculate what the determinant of A would be next. So to calculate the determinant of A, I'll do that up top. So let's do cofactor expansion along the first column because we have a 0 there. So it would be, let's see here, 2 times 1, 4, 5, 9, minus 2 times 2, 6, 5, 9. Be 9 minus 20, negative 11, so negative 2, so negative 22. And this would be 18 minus 30, so negative 12, times negative 2, so plus 24. So I think determinant A is 2. All right, so then looks like the system of equations would have been, the solution would have been X1 is 2. X2 is negative 1, and X3 is positive 1. And then you can kind of double check if you need to make sure that that was correct. So here's A, and this was B. So we can kind of check if we do like 2 times x1 plus 6 times x2 plus 2 times x3, that does equal 0. And then so on and so forth if you wanted to double check your answer, okay? So that would have been Cramer's rule. All right, so then I'll go ahead and clear the board, and then we can talk about part B. Okay, so we already found that determinant of A was equal to 2 earlier. So to get the inverse using this formula, so we need to calculate the matrix of cofactors. So that's what C would be. Okay. All right, so the cofactors were just like well, okay, so the 1, 1 cofactor is crossed at the first row and the first column. And then it'll be the determinant of this 2 by 2. So we need the determinant of that 2 by 2 matrix. And then for the next cofactor, cross out row and column. Take the remaining 2 by 2. And then this cofactor will have a negative in front of it. So to keep track of whether you should put a negative in front or not, you can kind of remember it by creating like a little picture, which I'm going to do up here. So start with a plus sign for the first entry. And then I'm going to alternate sign along the column. After that, I'll alternate sign along each row. So if I have plus, then alternating will be minus and then plus. And then here, since I have minus, I'll alternate, so next will be plus and then minus. And then since I have plus here, I'll alternate, so it'll be minus and then plus. Okay. So then I'll need to put a negative sign in front of these four to get the cofactors, okay? So that's why I put the minus in front of this one. So the next one, cross out, row and column. So 1, 4, 5, 9. And then next one would be minus. Cross out column and row, 6, 2, 9, 0. Next will be cross out second row, second column, 2, 5, 2, 0. Next one has a minus in front, and that'll be 2, 6, 5, 9. Next one, cross out column, row, so 6, 2, 4, 2. Next one will have a minus in front. We'll have 2, 1, 2, 2. And then finally, we'll have 2, 6, 1, 4. Great. So let's just do these determinants real quickly. So first one is negative 18. This one's 10. Negative 11. 18. Negative 10. 12. 4. That'd be negative 2, and then 2. Okay. All right, so then with that, A inverse should be, the transpose of C over the determinant of A. So determinant of A was 2, and then we'll just transpose C, and that'll be that. Okay? All right, yeah, so then let's see here. Let's go ahead and move on to the next question then. Okay. All right, yeah, so here we have a symmetric matrix, and we're trying to find its spectral decomposition. Okay, so then we'll first find the eigenvalues of A. So I like to do determinant of lambda I minus A for that. So I'll have lambda minus 2 along the diagonal. And then since I have minus A, I'll have plus 1 and plus 1 here. So that will give me lambda minus 2 squared minus 1. And then eigenvalues are the roots of this polynomial, so I'll set it equal to 0. Move the 1 over. That gives us lambda minus 2 is plus or minus 1. So lambda could be 1 plus 2, which is 3, or negative 1 plus 2, which is 1. Okay. So then for each of the eigenvalues, starting with lambda equals 3, to get the eigenvectors, we'll look at 3i minus a. So we can plug in 3 for lambda, which will just give us 1, 1, 1, 1. Okay. And then you want to find the null space of this matrix to get the eigenvectors. So essentially, we have just one equation for the null space, x1x plus 1y is 0. So I guess if I were to parameterize and say like y is t, so x is negative t. So then ignoring the t and just looking at the coefficients, so negative 1, 1 is going to be one eigenvector. I'll do the same for the second eigenvalue right now. So with lambda equals 1, I'll do 1i minus a. So plug in 1 for lambda. So it'll be negative 1, 1, negative 1. Okay. So that would just give us like a minus x plus y. We set it equal to 0 for the null space. So if that's y is x, so that would give us an eigenvector of 1, 1. And so for the spectral decomposition, you need to make sure that your eigenvectors are orthonormal. Okay. Now, remember that the eigenvectors corresponding to distinct eigenvalues are already going to be orthogonal to each other for a symmetric matrix. So that means you can kind of double check that your answers are good by checking that they should be orthogonal to each other, which they are in this case. So then to make them orthonormal, you just need to normalize each of them. So I'll just take those vectors and divide each of them by their magnitude. So dividing each of them by square root of 2, okay, and then putting those results into a matrix as columns, that gives us a matrix Q. Your capital lambda is just the usual diagonal matrix with the eigenvalues across the diagonal. And then with that, Q times lambda times Q transpose would give you the spectral decomposition of A, okay? All right, any questions about that? All right, so let's look at the next question. Okay, so testing for positive definiteness. Okay, yeah, so I talked about this in my review earlier, but for those who are new, so a symmetric matrix is positive definite if all of its eigenvalues are positive. So that's one way that you could test that these are positive definite by trying to find the eigenvalues to see if they're all positive or not. However, there's a theorem that allows us to test for positive definiteness without finding the eigenvalues. So I'll go ahead and just mention that theorem again. So if you have a symmetric matrix, okay, so I'm going to define A sub k to be the upper left k by k submatrix of A. Okay. So the theorem says that A is positive definite if and only if the determinants of each of these upper left submatrices of A, if and only if, they are all positive. Okay. So let's apply that result to the first one. So matrix A was 2, minus 1, 0, minus 1, 2, 0, 0. Whoops, sorry, that was minus 1. So minus 1, and 0. Okay, so I'm going to look at each of the upper left submatrices. So A1 would be the 1 by 1 upper left submatrix. So it's just this scalar 2, which is positive, so that's good. Now A2 will be the upper left 2 by 2 matrix. So 2 minus 1, 2. So we want to compute its determinant and check if it's positive. So determinant is 3, which is positive, so that's good. And then finally, A3 would just be the upper left 3 by 3 submatrix, meaning A3 is A itself. And you know what? I keep writing zeros for some reason. That was a 2, wasn't it? Okay. So now we need the determinant of A to check if this will be positive or not. So let's just do the cofactor expansion along the first row. That'd be 2 times 4 minus 1, so 2 times 3. Minus a negative 1, so plus. And then it'll be times negative 2 minus 0, so plus negative 2 ultimately. So that's 4, which is positive. Okay. So all of the determinants were positive. So according to this theorem, this matrix A is in fact positive definite then, okay? So that takes care of part A. And then part B is going to be similar. So let's see here. Part B is it's the same matrix except that the zeros in the two corners are replaced by B's. All right, so let's pretend that these zeros were not zeros anymore, but just B's. Now, incidentally, A1 and A2 are the same, so they're already both positive. But for this to be positive definite, we're now going to need determinant A3 to be positive as well. So let's go ahead and recompute what the determinant of A3 would be if we had B instead of 0 at these two locations. So again, the cofactor expansion along the first row will give me 2 times 3. But next we'll get plus 1 times, and then we'll have this 2 by 2 remaining. I'll go ahead and write it out. And then next we'll have plus B. And then we'll have this for the remaining 2 by 2. So let's see here. That's going to be 6. It's minus 2 plus B. And then here, this would be 1 minus 2B. Now distribute the B to that, so we'll get this. And then we need this to be positive in order for the matrix to be positive definite. So let me see what that gives us right now. Negative 2b squared plus 2b plus 4 must be greater than 0. Let's divide that by negative 2. So b squared minus b minus 2 has to be less than 0 then. Let's see here. I'll continue my work up top, okay? So I can factor that as b minus 2 times b plus 1. And we're looking to see when is this going to be less than 0. So to check that, we can just create a small sign chart. Just pretend that you're in calculus again. Choose your test points in each of these intervals. Plug the test points into here. So plug in negative 2, it's going to be positive. Plug in 0, it'll be negative. Plug in 3, whoops, negative. If you plug in 3, it's going to turn out to be positive. All right, so then from that sign chart, we see that this will be negative only when b is between negative 1 and 2. So if b is in the interval from negative 1 to 2, then the determinant of A3 down here should have been positive. And so then for these values of b, we could say that t would be positive definite, okay? All right, so any questions about that? All right, so let's go on to the next question. Okay, so we need a full singular value decomposition. So right now, matrix A is 3 by 2. So n is smaller than m. So it'll be easier if I start with calculating A transpose A. So let's do that first. So that's going to be 2, 0, very nice, okay. Oh wait, the last one is 1. Okay. So incidentally, since it's diagonal, we can already read off the eigenvalues as being 2 and 1. Okay. For SVD, go ahead and order the eigenvalues from largest to smallest. That's not super important, I suppose, for finding an SVD, but that's what people usually do in applications, so I think we should follow that convention. Okay. So then we need the eigenvectors next. Oh, and maybe before I continue, so let's see here. For the full SVD, so full SVD will be factoring A as U times sigma times B transpose. And if A is 3 by 2, then U will need to be 3 by 3. Sigma will need to be 3 by 2, and B will need to be 2 by 2. So we'll keep those in mind. Okay. So we can get V by finding the eigenvectors of A transpose A right now. So let's see here, when lambda 1 is 2. So if I look at 2i minus A transpose A, that's just going to be 0, 0, 0, and 1. So that leaves me with 0x1 plus 1x2 is 0. So x2 is 0, but x1 will be free. So that gives me one eigenvector, 1, 0 right now. If we just check the next one, lambda 2 is 1. So 1i minus A transpose A. So this time it'll be negative 1, 0, 0, 0. And then x1 will be 0, x2 will be free. So you'll get 0, 1. Okay. So they are already orthogonal to each other, as they should be, being eigenvectors corresponding to distinct eigenvalues of a symmetric matrix. And they're already unit linked as well, so we actually don't even need to normalize them. They're already orthonormal. So these guys should constitute the columns of matrix V. So it looks like V is actually just an identity matrix for this problem. Okay, so we have V. We can actually calculate sigma already just from the eigenvalues here. All right, so remember that if you square root the positive eigenvalues, that gives you what we call the singular values of A. The square root of 1 is 1. So then for sigma, what you do is you take the singular values and you put them into the diagonal of a matrix. And then after that, you're going to add zeros as needed to make it the same size as A. So to make it 3 by 2, I need to add an extra row of zeros. All right, so that will be sigma. Now to get U, So that one will take a little bit of work. Okay. So first we had these formulas. Oh, let's see here. Okay. So then from the V's that we calculated here, we can use them to calculate some of the U's that we need for matrix U. So we had these formulas where U1 will be 1 over sigma 1 times AV1. And we can get U2 as 1 over sigma 2 AV2. Okay, so let's see. So U1 would be 1 over root 2 A times V1, which would be 1 over root 2 times 101. And then similar for U2, so that'll be 1 over 1. And then A and then V2. So that's just going to be 0, 1, 0. So then we can go ahead and put these into the columns of U. Whoops, positive. All right, but for the full SVD, our matrix U has to be 3 by 3, since A was 3 by 2. So we are missing one column. So then to find U3 and get this last column that we need, okay. So in general, if you, after doing this, using these formulas, if you need some more U's to fill out the matrix U, the remaining U's can be found by finding an orthonormal basis for the null space of A transpose. Okay. So I will go ahead and do that. So here is A transpose. So to find its null space, we have x plus z is 0 and y is 0. So let's see here, y is 0. If z is t, x would be negative t. Okay. So then that would be a basis for the null space of A transpose. So let's see here. If you had more than one basis vector, you might need to do Gram-Schmidt to make them orthogonal. And then once you make them orthogonal, you would normalize each of them to make it orthonormal. But in this case, we just have this one vector for U3. So this would go into the third column for matrix U. And then with the matrices sigma, V, and U that we calculated, you'd have A equals U sigma V transpose, and that would be the full singular value decomposition. Okay. All right. So any questions about that? All right, in that case, let's go ahead and look at the last two questions. All right, so let's see here. All right, so for this matrix, let's see. So we kind of have an LU factorization of sorts for matrix A, although A looks like A was not a square matrix. So rather than getting an upper triangular, we just have a row echelon form instead. But since this is a row echelon form of A, we can see that the first two columns have pivots. So that means that the first two columns of A would form a basis for the column space. And we can calculate the first two columns of A without calculating the entire product. So if we just calculate L times the first two columns here, that would have given us the first two columns of A, okay? So let's do L times 1, 0, 0. So if you do that, you'll get 1, 6, 0. So that would have been the first column of matrix A. And then if you just multiply L with the second column, so times 2, 1, 0, that will give you the second column of A. It's going to be 2, 13, and 1. Okay. So then these two vectors should form a basis for the column space of A. Okay. All right, so again, the idea is once you see which columns have pivots in the row echelon form, you take those columns, but from the original matrix A to get a basis for the column space. In this case, to find what the first two columns of A were, we just multiply L with the first two columns of R, okay? All right. So next, to get a basis for the row space, which is the column space of A transpose. Okay. So you can get a basis for the row space by looking at any row echelon form of A, and just take the non-zero rows of the row echelon form, and those guys would form a basis for the row space. All right, but I write them as columns just because we usually think of vectors as columns, but also because technically the row space is the column space of A transpose, so kind of thinking of it as columns for that as well, okay? All right. Now, to get a basis for the null space of A, we can also get that by using the row echelon form right now. So let's see here. From the row echelon form, so I will go ahead and from the matrix R, let me just do one small row operation to make it a little bit nicer. So I'll do row 1 minus 2 of row 2 to get it into reduced row echelon form. Yeah. So if I do that, let's see here, it will be 3 minus 4 will be negative 1. And then the last one is 4 minus 6, so negative 2. Okay. So then from the reduced row echelon form of A, here's the corresponding system of equations that we get for the null space. Oops. And so here we're going to have, we're going to have two free variables. Let's choose x3 and x4 to be free. Since the third and fourth columns don't have pivots, so that would be a good choice. Then x1 would be s plus 2t, and x2 we could say is negative 2s minus 3t. So then if I just extract the coefficients of s and put them into a vector, and then extract the coefficients of t and put those into a vector, this would be a basis for the null space. Okay. And then finally, for the left null space, the null space of A transpose. So there's not really a particularly easy way of getting that from the row echelon form or anything like that. But what you can do to get the null space of A transpose is to take the basis that you found earlier for the column space of A. So earlier, the basis for the column space of A, we had the vector 1, 6, 0. And then we had 2, 13, 1. So I take the basis vectors for the column space and put them into a matrix as rows. Writing them as rows because I'm kind of looking at the transpose, if you will. And now I just need to find the null space of this matrix, and that would give me the null space of A transpose. So to get the null space, let's just do some row operations real quickly. And then I guess that's good enough. So that gives us 1x1 plus 6x2 set equal to 0 for the null space. And then x2 plus x3 equals 0. Let's choose x3 to be free, since the third column has no pivot. X2 would then be negative t, and then x1 would be positive 6t. So that the vector 6 minus 1, 1 would be a basis for the left null space. Okay. All right, so any questions about that? All right, great. So then we'll just look at the final question. Oh, it's a bonus. So A is skew symmetric or anti-symmetric. All right, so let's look at part A first. Okay, so we want to show that x transpose AX is equal to 0 for part A. So here's what I'm going to do. So first, let's note something. So A is n by n, right? X is a vector in Rn, so size n by 1. So x transpose would be size 1 by n. So it is good just to sort of verify x transpose AX does result in a 1 by 1, meaning it is a scalar, okay? All right, and specifically we want to show that it'll actually be equal to the scalar 0. All right, so here's how we can do that. To make use of the fact that A is antisymmetric, let's consider what happens when we take the transpose of X transpose AX. Now, on the one hand, X transpose AX is just a scalar, just a 1 by 1, so its transpose should be itself. So on the one hand, its transpose is equal to itself. But on the other hand, we know that when you transpose a product, that you can transpose each factor, but then you also reverse the order of everything, meaning the transpose of this should be X transpose first, then A transpose second, and then X transpose transpose, it's just X last, okay? So therefore, these should be equal to each other. And then let's see here, since A is antisymmetric, we know that on the right-hand side, A transpose is negative A. So you can write it like this now. So therefore, we have a number which is equal to the negative of itself. And the only number which is equal to the negative of itself is the number 0. So therefore, we conclude that X transpose AX is 0. And that was for any arbitrary vector X. Okay? All right, so then next, we want to also show that the eigenvalues must be purely imaginary. Okay, so at this point in the review, I struggled for a couple of minutes, about 20 minutes actually, trying to prove this result. And ultimately, my proof of this result in the end, something bothered me about it. Something seemed wrong about it, but I couldn't quite see what was wrong. And so therefore, I sort of accepted maybe it's right. But then after the review, I did take a closer look at what I did. And upon closer inspection, I see that it was not quite right. So the work that I did wasn't exactly wrong, except at the very end when I made the wrong conclusion. But the problem with my work was it did not prove the desired result. It proved something else, which I didn't realize at the time. But what I'm doing now is I'm going to prove this result, and the proof that I give is going to be actually correct, okay? So let's talk a little bit about complex numbers first. So Z is a complex number. Then it can be written in the form A plus IB, where A and B are real numbers. Now, associated with a complex number is its complex conjugate, which we denote with a bar on top, so Z bar. The complex conjugate of a complex number is A minus IB. Likewise, the complex conjugate of A minus IB would be A plus IB. So all it's doing is just changing the sign in the middle. Okay. Now, a purely imaginary complex number, this would be a complex number of the form IB. So in other words, the A would be 0, and it would just be I times some real number. That's what a purely imaginary number is. Okay. Now, we also want to consider complex vectors for this problem. Okay. So similarly, a complex vector can be written in the form u plus iv, where u and v are both real vectors, so say vectors in Rn. Okay. And then likewise, we can talk about the complex conjugate of a real vector, so x bar, and it works in exactly the same way. You just change the sign in the middle, okay? All right. Now, one thing that I want to note about a complex number and its conjugate, as well as a complex vector and its conjugate. So notice if I take z and I multiply with its complex conjugate, okay, if we were to FOIL this out, we would get a squared minus iab plus iab, so those would cancel out. And then here you're going to get minus I squared b squared. Now I squared itself is -1, so minus I squared b squared is actually plus b squared, okay? All right, so this is the magnitude of the complex number z squared. Okay. So I guess real quickly, the magnitude of a complex number, if z is a plus ib, its magnitude is square root of a squared plus b squared. Okay. So then z times its complex conjugate gives us its magnitude squared. All right. And there's something similar with complex vectors as well. So if I do x transpose times let's see here. I'll do x conjugate transpose times x. Okay. Okay, so how is this going to work? So x conjugate is u minus iv. So we have that transpose times x, so times u plus iv. And when I have u minus iv transpose, that is the same as u transpose minus iv transpose times u plus iv. And then if I FOIL this out, we'll get u transpose times u plus I u transpose v minus I v transpose u. Those are going to cancel out again. And then we are going to get minus I squared, which will give us plus v transpose v. Okay. Now, u transpose u is the same as u dot product with u. So that's the same as the length or the norm of vector u squared. And likewise, this is the norm of vector v squared. Okay. And incidentally, this is how we define the norm of the complex number x squared as well. Or I guess you can say it's the same as the norm of the vector x squared. Okay. Okay. So those are just a couple of things that I wanted to highlight before I dive into the proof. So again, I'm trying to prove that if A is real and anti-symmetric, then its eigenvalues are purely imaginary. So let's jump into the proof now. So let's suppose we have an eigenvector x and a corresponding eigenvalue lambda. Okay. Now, so we're trying to prove that lambda is purely imaginary. So at the start, we should assume at least that lambda is complex. Okay. Now, for those of you who were in my review, the error in my proof is that although I was treating lambda as if it were a complex number, I was treating x as if it were a real vector. But if we are considering a complex eigenvalue, then we also need to consider that the eigenvector may be complex. So therefore, I should think of x as being a complex vector. So the form u plus iv, where u and v are vectors in Rn. Okay. Now, what I want to show, that A would be equal to 0. Because if A is equal to 0, that would mean that my eigenvalue was purely imaginary. Okay? All right. So let me rewrite AX equals lambda x as I replace x with u plus iv. And then I will replace lambda with a plus ib as well. Okay. All right, so there are two things that I want to do with this equation. Okay, so the first thing that I want to do I want to multiply both sides of this equation by the conjugate transpose of the eigenvector. Okay, so conjugate becomes u minus iv and then transpose. All right, so I'm going to multiply both sides on the left by the conjugate transpose. So that's going to leave me with this right now. Okay, now this is a complex scalar, but as a scalar, I would be able to keep it in front and then multiply the conjugate transpose of my eigenvector in the middle. Okay. So when I do this, so let me kind of shorthand this a little. So let's see, this part on the left is not super important, so I'm gonna just write it as x conjugate transpose ax. Yeah. Now on the right here, I'm gonna continue writing the eigenvalue a plus ib. And then here, where I have u minus ib transpose times u plus ib, we did this computation earlier where it turns out to be the length of u squared plus the length of v squared. Okay. So just real quickly, that's what I did up here. All right. Okay. Now I'm going to leave that for the moment, and now I'm going to do something else to this equation. So what I'm going to do right now is I'm going to transpose both sides of the equation. So when I transpose the left-hand side, we'll get u plus iv transposed first. Then times a transpose. And then on the right, okay, so a plus ib, again, that is a scalar. So nothing happens to it when it gets transposed. And I can continue writing it in the front. And then I am transposing everything on the right-hand side, so I also need to transpose the u plus iv. Okay. So now after that, I need to, what I'm going to do next is after transposing both sides, what I'm also going to do now is I'm going to apply the complex conjugate to both sides of this equation. So when I complex conjugate the left-hand side, so this will become u minus iv. Okay. Now A is assumed to be a real matrix, so there are no complex numbers in A, and therefore the complex conjugate has no effect on A transpose. Now, on the other hand, on the right-hand side, I guess I'll make a quick mention that when you complex conjugate a product, whether it's a conjugate of two complex numbers, or if you complex conjugate a complex scalar times a complex vector, complex conjugate has a property that you can just transpose each individual term and then multiply the results. Okay. So what that means is when I complex conjugate the right-hand side, I just need to complex conjugate each term. So conjugating the complex number, and then here conjugating the complex, vectors over here as well, okay? Okay, so I transposed, and then I took the complex conjugate of both sides. All right, now, I guess what I'll do next is A is assumed to be antisymmetric, so let's go ahead and replace A transpose with negative A. Okay. Yeah, so A transpose is negative A because A is antisymmetric. And then what I'm also going to do right now, I'm going to go ahead and multiply both sides by a negative. So that I'll move that negative over to this side, okay? Now, the last thing that I'm going to do is I'm going to multiply both sides of this equation on the right. By u plus iv. Okay. So let's see what happens when I do that. So on the left, I have this x conjugate transpose ax again. And here on the right, I have negative a minus ib. And then this stuff, just like up here, or it's the same as up here. Okay. So it all multiplies out to be the norm of u squared plus the norm of v squared. So now I'm going to, let's take a look at the two results that we got. Okay. And let's see here. Okay. And then let me go ahead and before I do the comparisons, I guess, just to make it a little bit easier to write, let me go ahead and rewrite this in parentheses just as the length of x squared. Because this part is actually not too important anymore either. Okay. Okay, so now I'm going to rewrite the two results that we just observed. So result number one was that x transpose ax equals a plus ib times the length of x squared, or that was x conjugate transpose. Okay, x conjugate transpose. And then contrasting that with result number two, which says that x conjugate transpose and then times ax is negative a minus ib and then times the length of x squared. Okay, so I have two expressions for x conjugate transpose ax. So that means these two must be equal to each other. Okay, so let's go ahead and set them equal to each other then. A plus ib times the length of x squared equals negative a minus ib times the length of x squared. Now to make this more clear, I'm going to go ahead and I will distribute the length of x squared into the parentheses. So then distributing will leave us with that. Okay. So now on the left and right hand side, we have two complex numbers. And for two complex numbers to be equal to each other, their real parts must be equal to each other, and their imaginary parts must be equal to each other as well, okay? So in other words, a times the length of x squared must equal negative a times the length of x squared. So that's equating the real parts together. And then their imaginary parts are already equal to each other. So, I mean, I guess I'll write it up, but I mean, that's kind of already the case, so we don't need to concern ourselves much with this. So this is good. All right, but let's see, what does this tell us, though? Okay. So here we have, so remember that a is a real number, and the length of x squared is also a real number. So, I mean, that didn't even matter, but we have a number that's equal to the negative of itself. And the only number, real or complex, that is equal to the negative of itself is 0. So therefore, we see that a times the length of x squared must be equal to 0. Well, that leaves us with two possibilities. So that means either a is 0 or the length of x squared is 0. Okay. But we can rule this case out, that the length of x is not going to be equal to 0. The reason why we can rule this out is because x was assumed to be an eigenvector of A, and eigenvectors are by definition non-zero. And so therefore, we have proven that A must be equal to 0 then. Okay. And if A is equal to 0, let me try to squeeze it all. Well, okay. That's annoying, but okay. So A being equal to 0 is what we were trying to show. Okay. So A being equal to 0 means that our eigenvalue was of the form IB, so it was purely imaginary. Okay. Okay, now I honestly don't think this was really important, but maybe for those of you who were interested in seeing the proof of this result, that was it, okay? But in as much as you guys didn't really do anything, I don't think, with complex numbers or complex eigenvectors, I don't think you need to worry about this too much. This was a bonus question, so I don't think it was that important to the professors either, if you could do it or not, okay? But that's the result. I just wanted to correct what I did in my review, so, all right.